Good morning, everyone. I'm here to talk about living on channel ZGC, which is a garbage collector. So if you're not interested in garbage collectors, this is not a talk for you. So what I'm going to be talking about is, first of all, a small introduction to garbage collection, just to refresh that. Talk about ZGC in particular and how it works. ZGC on AR64 in particular. Some things about performance and what remaining work there is to be done. But before continuing that, why am I here? So when features are introduced into OpenJDK, if there's hardware-specific implementations, it tends to be done only on x86 64 by Oracle. Other platforms need to be done by other people, and of course, myself working for Linaro and such like, I've taken upon myself to do ZGC. And there's been other features too that have been implemented by non-Oracle so that there is support on AR64. And one other reason is that performance is affected by features. Garbage collection isn't something you necessarily have to do, but it is something that is very fundamental to performance. Excuse me. So, ZGC, quickly. It was an experimental feature that was introduced on x86 64 in JDK11, JEP 333, and it's a region-based concurrent copying garbage collector. Don't worry if I'll explain what that means. But basically, it allows you to have very large heaps. The goal is multi-terabyte heaps, but have a pause time for garbage collection in the order of about 10 milliseconds or less, with at most a 15% reduction in throughput. If you want to know in more detail in what I'm going to explain, have a look at the ZGC wiki. They have several presentations that go into more detail over a longer time into how it actually operates. So, garbage collection. Garbage collection is simply automatic memory management. The responsibility of freeing objects is taken by the runtime as opposed to the program. And one way of doing this is to follow the graph of live objects, and anything that you can't reach is garbage. One way of doing this is through a mark and speak algorithm. Here I have a couple of threads. They have their own stacks. There's references from the stacks into the objects graph. And here we see references from stacks to the circles, which are objects. The red triangle of circles are objects that are not reached and would be regarded as garbage. Observe that we don't do reference counting, so those objects pointing to each other in the red triangle won't survive. This particular garbage collector that I'm showing here is a copying collector. So objects are allocated in the from space, and when garbage collection executes, they get moved over. I'll just show that here. So anything that's been marked as live is copied over. Anything that's not copied over is implicitly gone. There's another ZGC cycle, the from space is reversed with the to space, and again, they're copied back and forth. There are other garbage collection schemes, but this is for illustration. Now, when we're moving objects back and forth, that can be very upsetting to programs if you change the pointers of the structures that you're executing against. So this tends to be done when the program is stopped and the references are updated at that point. Which brings us neatly to the concurrent copying collectors. Concurrent copying collector is very much like what was in the previous slide, but rather than copying objects and updating the references when the program is stopped, they're copied and moved as the program is executing. This requires some magic to get working. Now, ZGC isn't the first instance of a concurrent copying collector. Shenandoah was finally merged in OpenJDK 12, which was developed in Red Hat. Going further back, the Zulzing VM had the continuously copying concurrent collector. Yep. And more recent on your Android devices, the Android Art runtime is a copying collector, or concurrent copying collector. And that is useful because pauses are very visible when you are updating screens. So if you're pausing for more than 16 milliseconds, screen starts stuttering. So that's the reason for that. And there's been lots of research into this too. There's PC Stopless from IBM, there's Staccato, there's another one called Sapphire. And so now we have ZGC from Oracle. Now, cast your mind back to the from and to copying collector. Very much like G1GC, rather than doing that operation on the entire heap, each garbage collection cycle, you can split the heap up into a large number of pages, regions. And so you can choose which pages you want to then copy from, depending on how much garbage they've got. And so rather than pausing and going through the entire heap, you can do these regions. Now, unlike some collectors, the heap is very sparse in terms of the virtual address space it occupies. So we've got a 4 terabyte virtual address space size, but only up to your maximum heap size of worth of pages will actually be allocated at any given time. And it means if you come along and allocate a large array spanning multiple pages, then you will have space for it. The current limit's 4 terabytes, that may be increased in future. Now, this is something I'm explaining for the purposes of what will come afterwards. Now, if you've moved objects out of a page, take it as read that when you're doing this concurrently, you will want to understand where the objects have gone while things are being fixed up. So in a forwarding table, on the left-hand side, we've got a page that wants to be relocated, and the right-hand side is a new page in which the objects have been copied. And while things are being updated, you'll get a reference to the old page, for which you can look up the forwarding table and find out the new addresses of objects that have been moved. This will become important. Another element are the coloured pointers. So normally, objects point to other objects with just plain pointers, an address in memory that's opaque to the Java program. What we do is we add some metadata to those objects that allows us to track what's happening to the object graph as operations are operating concurrently. Simply put, you can have an object reference, and if we examine it, we can see that it's bad at some point, and then we can update it. The forwarding table could be examined to then get you a good reference. So we have a bad reference, check the address is wrong, we look at the forwarding table, we update it to a new pointer. So in more detail, in the ART64, I've taken the decision to use the top byte ignore bits. What this means is that these bits have no significance in terms of addressing. They are ignored, but we can put the bits that are significant to ZGC there. x86 is another technique I'll explain slightly a wee bit later. Solaris Spark had an initial ZGC port that's not been merged upstream, but they use very much a similar technique, which is VA masking. Yeah, it's essentially the same thing. Now, bear in mind everything that's gone on so far. We have things called load barriers. Now, these are not load barriers like we have in our memory model. So they're not DMBs, they're not LDARs or anything of that ilk. And they're not compiler barriers. These are GC load barriers. And what this means is whenever you load a reference, you do some additional work. Example I give here is we've got object X, so that's a reference, and it's retrieving it from field Y in object O. So we're loading a reference. And there's other instances too. Now what this looks like on AR64 is, first of all, we have to get an idea of what a bad reference looks like. So we're loading that from the thread pointer x28 into x11. We're loading the object reference into x10 here from some other object, and then we're doing an AND and a compare and branch. Most of the time, you won't get a bad reference, you'll get a good reference, and so you continue on with a good reference. If you've got a bad reference, this will then branch to a stub, which will then do the fixing up of that reference. That's a bit of a duplicate. On x86, they don't have top bit ignore, so they map the heap into multiple places in memory. Running this on my laptop on x86, htop reports about 17 terabytes being used. A little disturbing at first. On the ARC64, of course, we cut that out. We just have a single 4 terabyte address space. There should be less of a hit on the TLB, although only one address space is significant when normally used. And in principle, we could have 4.5 petabytes. Although if your Java program is getting that large, you've probably got other problems. So, how are we doing? Right. Putting it all together, we have regions, the Z pages that contain objects. References between those objects are coloured, so we can tell if an object has been marked. Have we encountered it before? We can tell if an object needs remapping. So if an object hasn't been marked, we might change its position. We might update the reference. And Z pages have forwarding tables. So given an old reference that's bad, we can make a good reference from that. Right. Everyone with me? Excellent. So this is the circle of life for ZGC. There are pauses in ZGC, and we have to do that at certain places. So when we start at the top of the circle, we do a mark start. So we start marking. There we mark all of the roots. Ostensibly, these are all in the thread stacks, from the thread stacks into the heap. So we have to pause the program to do that. After having done that, we then do a concurrent map and concurrent remap. So the garbage collector threads are traversing the object graph and marking objects. Objects that are marked are the ones we know are live. Objects that are not marked are objects that are dead. Concurrent remap I'll get into a second. After finishing marking, we will then do some preparation to do the relocation of objects. That is, moving them from one page to another. Mostly, that's about choosing which pages. So we go over the pages and decide which ones are candidates for being emptied. So the ones that are full, but full of garbage. And so there's a priority list of which ones we should do there. And then we start doing relocation. So the program is executing during these concurrent regions. During concurrent relock, the program is executing while we're moving the objects. Then we get to mark start again. We'll then start traversing the object graph again. And what concurrent remap does is we're then updating the pointers from the old bad pointers of the relocated objects to the new object addresses. The load barriers come into play at these concurrent regions too. So when we're doing remapping, if a load barrier encounters a bad reference, it will find a good reference and then keep executing. And this is where we race between the JVM, well, the program threads and the GC threads. So there's a compare and exchange that goes on at the coloured object pointers to make sure one of them will win. Now one of the things that helped doing this is that there are a very large number of, well, there's a lot of GC algorithms in OpenJDK. Serial parallel, concurrent merge and sweep, G1 Shenandoah, and now ZGC. And all of this impacts C1, C2, the interpreter, and a lot of the other C++ code. So to change and add a new garbage collector requires changes in lots of places. This API made that very much more tractable. Doing AR64 meant implementing some of these APIs for that garbage collector for that platform. Other things we found in ARC64 is our literal addresses. So we have references to objects in generated code. Previously they were 48-bit. So I've added a flag to make them 64-bit, so the color's not lost. That was quite an invasive change, but it seems to be working. It has the side effect as well as it would be able to help enable the 52-bit virtual addressing. Initially I did that for just literal loops, but I've changed that to do everything that's an address off of the generated code. The memory model looks okay so far. This is our memory model. We're doing concurrent updates of things. We have to be careful that threads can agree upon what the heap looks like at any given time, where that's significant. The load barriers themselves fix up things with a full memory barrier. And that should be okay. So, some caveats here. I'm going to talk about performance. This work is not done and dusted and completed. I haven't managed to merge it just yet. But it can be useful to do performance just to see if we're on the right track. Performance figures might vary at a guess. It could be like 30% better, 30% worse. There's no guarantees. But so far, it's looking quite good. I'm running spec JBB. I'm not doing any particular tuning to get the most out of any particular garbage collector. This is just out of the box. If you've got experience with other garbage collectors, the tuning of ZGC is very straightforward. There's two knobs, the size of the heap and the number of garbage collection threads, and that should be enough. So here I'm comparing G1GC, which is the default garbage collector, Shenandoah, which is a new concurrent collecting garbage collector from Red Hat, and ZGC as it is. And all of this is on the same machine on ARC64. Now, the max JOPS is the maximum throughput we can get during the spec JBB tests. And as expected, we get less performance with the garbage collectors with load barriers. However, what's interesting is the critical JOPS, which is the throughput with given latency guarantees. G1 can't reliably give, well, we get less performance at a given latency from G1GC and Shenandoah, and ZGC is looking very promising there. You don't use ZGC for the absolute throughput, you use it for the latency guarantees. Graphing the performances, this is a log scale, so this is ranging from single-digit milliseconds up to 4,000 milliseconds. And we see these spikes here, which are generally undesirable if you're doing online transaction processing of the sort. Shenandoah is way better, back to a linear scale. So we've got down to 34 milliseconds for the maximum pause, and a mean of about 4.6. And ZGC is better in terms of max, 22 milliseconds as opposed to 34 before. Not quite 10 milliseconds, which is the goal, but it's certainly looking promising just now. Shenandoah and ZGC might be more comparable if I'd done more runs. Maybe there was a spike here and there, but it looks okay. So, remaining work. My goal is to get this upstreamed as best I can. Bug fixing, testing, more reviews. C2 still needs some fixing in terms of some of the verification flags. Testing, and even more testing. The ZGC garbage collectors tends to vary in their behavior depending on what you're executing. And some debug APIs need to be aware of the TBI. And ZGC continues to be developed, so I'm tracking what's going on there. The next thing to do is to be able to unload classes concurrently, and they've got that merged upstream. Some special code that needs to be there. And there's Graal support that needs to be added. So, in summary, there's some benefits to having ZGC on the ARC64. I think it would be well worth having it. Still some work to do, and there's definitely some promise for further optimization that I've identified. So there you go. Thank you. Any questions? Alex?
This might just be my unfamiliarity with how Java objects live, but is there when a thread is actively working on an object, does that mean it can't be garbage collected?
Yes.
Right, okay,
So when you have your routes marked, the thread stack will have a reference to the object you're operating on. And so that will be marked as live, so it's not going to get collected.
So it'll stay in its place?
Yeah, it'll stay in its place. Or it will pause, it will get moved, but it will still keep executing against the new reference.
Well, one doubt about how about your test hardware environment when you just show that benchmark values, some last slides. What hardware platform?
It's not ThunderX1, so we've got dozens of cores and out of order cores at that. So the actual numbers themselves are not too interesting.
Running gigahertz, it's 2.5 gigahertz, the CPU frequency.
It's multiple gigahertz. Again, it's not too interesting. If you want to try this, my patches are on the ARC64 dev mailing list, and you can try and compile it. But yeah, the numbers aren't too interesting just now.
Thank you.
Chris.
This is not a ZGC, a specific question. Do you expect to see differences in behavior for garbage collection for natively compiled Java compared to other languages that are compiled to the JVM?
There's always differences in behavior there. To give an example, if you have some dynamic languages where classes are generated at runtime, then perhaps the class unloading, if that was enabled, would benefit it. But yeah, it could vary as much as by how your program is written, as well as the language on top and how you're executing it. Yeah, it's an interesting one. So I'm trying to think of the languages in which they will do things differently. Where I think maybe JRuby and the like, there can be more indirection. There may be more objects generated just from the get-go. But yeah, I would certainly expect there to be differences. Okay, if there's no further questions, thank you very much.